Hi everybody. So this is lecture 1, part 2 of homeostasis. So in part 2, we're going to do a few things here. We're going to learn which variables are homeostatically controlled. We're going to learn what the difference is between intrinsic and extrinsic controlled systems. We're also going to learn the difference between feedback and feed-forward mechanisms, and how each contribute to maintaining or modifying homeostasis. Okay, so let's get going. Hopefully this is going to help you study. We've got this nice smart woman here studying diligently, and I turned on the lamp above my head because I'm going to share some bright ideas with you. All right, let's get started. Okay, that was corny. Here we go. So if you recall from part 1 of this lecture, homeostasis was defined as how your body maintains fairly stable conditions so that your organ systems can function normally. Okay? And so we want to look at what are the different types of variables or the different things in your body that must be maintained homeostatically. So here's a list, and this is not an exhaustive list. You might think of other things, but we talked a little bit in the part 1 of this lecture about nutrient molecules. You need to have a certain amount of carbohydrates in your body, and lipids and proteins and nucleic acids. Remember, you learned those in general bio. I told you general bio was going to come back and haunt you. Okay. We also have to maintain a certain amount of oxygen in our body. We even maintain a certain amount of CO2 in our body. Even though we might consider it a waste product, later on we're going to learn what CO2 is used for when it's in the right concentrations in our body. Okay, waste products can be maintained at a certain concentration. We can't have too much of it though. When we do, homeostasis control systems will help us get rid of that waste. pH, we actually maintain a certain pH level in our body. The concentration of water in our body. We talked about water compartments in the last lecture. And so how much water in our body is very important, and that's also related to the salts and other electrolytes like potassium and things like that. We have to maintain certain levels of those variables. Water is very much related to the volume, right? So certain volume within our cardiovascular system, and that's related to pressure. So we have to have a certain amount of pressure, blood pressure. Okay? And then we also have to have a certain temperature in our body. So again, so these are just some of the things. You might think of other things. This is not the end of it. So there might be many other things. Okay. So I had mentioned that we want to maintain those variables and others in a fairly constant amount in our body. Okay. And so if we want to maintain a fairly constant amount, we have to, and have a range, we have to have an idea of what's kind of the middle point. That's what we refer to as the set point. This is like the average of the concentration of whatever variable that we're talking about. So I will use temperature as an example. What is normal body temperature? Hopefully you're saying 98.6 degrees Fahrenheit. If you think in Celsius, it's about 37 degrees Celsius. Okay. What happens though if your body is 98 degrees? Nothing. You're fine, right? Even if your body is 97 degrees, you're okay. But what if it goes the other way and it's 99 degrees? It's actually still okay. When you start to approach 100 degrees, then your body starts to detect that you're going out of homeostasis, and you want to bring it back down into homeostasis before it goes too far. High temperatures in your body, if you remember from general bio, can cause enzymes to denature. And if that happens, your body can't perform the correct chemical reactions. And the functioning starts to break down. So it's in our best interest to bring it back toward the set point. Okay, and again, we have some wiggle room there. It doesn't have to be exactly the set point, but we want to bring it back in there. If we start to get too cold, we're going to do things to bring it back up. Okay, so that's what I mean about maintenance of fairly constant internal conditions. You can have deviations around that set point, but within a normal range. We can actually tolerate lower temperatures than we can tolerate higher temperatures. So to be more accurate, this could even come down a little bit more, but we can't tolerate too many high temperatures. And again, that's mainly because the enzymes can denature. Okay. So we're going to get into that. Last slide said that it says maintained by negative feedback. So I'm going to get in more detail in just a minute. But I also want you to understand that an organ, when an organ system or an organ is starting to go out of homeostasis, it can either have a control system within the organ, or something can control the organ from outside. Okay, so this is the difference between intrinsic controls and extrinsic controls. So intrinsic, so think of that word, intrinsic. That means something is happening within the organ and it did not get a signal from outside of the organ. The organ is regulating itself. Okay, a good example of that is if you cut yourself, that cut will actually trigger a set of chemical reactions that will occur, a chain reaction that will start repairing the tissues in the skin and also repairing the capillaries and the arterioles and things to stop that bleeding and to prevent bacteria from infecting the cut. We didn't have to wait for the brain to figure out that, oh, we have a problem, we have a cut, we're losing blood. That might take a little more time. If the organ itself, the skin itself, can detect that there's a problem and start the chain reaction of chemical reactions and control itself, we're going to have that much of an advantage over repairing and cleaning up the wound. Okay? Now, other times, though, we have extrinsic controls. The organ will change its activity based on a signal, and it's always from an extrinsic control. The organ is always being controlled by the nervous system or the endocrine system, right? And the endocrine system does that with hormones. It could be both, too. So an example of an extrinsic control. Right now, you're at rest. I hope you're at rest. Maybe you're watching this on a treadmill, okay? But I'm going to assume you're at rest. Okay? At rest, your heart is actually being slowed down by nerves, okay? Because your heart will contract by itself, but it will set its own pace, and that pace is actually higher than what you need when you're at rest. So right now, here comes anatomy, the vagus nerve is actually causing your heart rate to slow down. Alrighty, so that your heart is being controlled by a nerve that's originating from the brain, right? So extrinsic control. Now, an organ might also have intrinsic controls. So it just kind of depends on the situation of what kicks in to control it. Okay, I'll give you more examples of these as we go. So you just want to keep in mind intrinsic and extrinsic controls. A lot of what you're learning now is going to be a theme throughout the entire semester. And understanding this will help you understand how different organ systems function. Okay, so I mentioned feed forward and feedback systems. These are systems that are going to help control that homeostatic control system, okay, and help maintain, or it might modify homeostasis. Okay, so the first one here is feed forward. Feed forward systems are not quite as common, but we do, these things do happen. So feed forward is the term that we use when your body is actually anticipating a change is going to occur. So that change hasn't happened yet, but signals are coming in that's preparing your body for a possible change occurring. Okay, so let me give you an example and then I'll tell you why we do this. A good example, so I want you to do this right now. I want you to think about your absolute favorite food. Is it gooey chocolate chip cookies and you smell that coming out of the oven? Maybe a favorite relative makes them for you. Oh, is it, I don't know, think of your favorite meal. Oh, baklava. I guess I have a sweet tooth. If that's not doing it, another thing that might do it is think of sour lemons. something really, really sour. Is your mouth watering now when I say that? Right? When your mouth waters, those are your salivary glands kicking in, and that is the first stage of digestion. We know digestion occurs when we bring food into our body and we have to break those large pieces of food into small molecules, nutrient molecules, so that they're small enough to absorb into the bloodstream and absorb into your cells. Okay, so that's why you salivate. That's the first step of digestion. But digestion occurs when you're eating. That's why you do it, right? You haven't put any food in your mouth and you're already starting digestion. You're anticipating that food is going to come. Digestion is a long process. It takes time. And so there's an adaptive advantage to this. If you can start the digestion process that much more quickly, if the juices get flowing in your mouth, and also you don't know this right now, but the juices are starting to be secreted in your stomach. Okay? So that means when the food gets in there, digestion is already starting, which means that the juices can get in there and start working on the food that much faster, that split second faster. And that can provide an advantage to you to get the nutrients in faster. So this doesn't maintain homeostasis, because if you're hungry and you start thinking of food and you're salivating, you might not get the food. So you didn't reverse the original condition. Okay, you're still hungry. You're still low in nutrients, whatever it is. Okay, but again, it's just a way to kind of modify homeostasis and maybe get back to homeostasis just a little bit more quickly. Feed forward, anticipation. Okay. Feedback refers to responses made after the change has occurred and it's been detected. Okay, so we're going to discuss two types of feedback systems, negative and positive. Now, usually we think of negative feedback as something, or negative as something bad, and positive as something good. That's not how this is being used here. Negative is referring to the reversal of an original situation. We mentioned temperature increasing. We're going to do things to decrease it. That's a reverse of the original situation. Okay, and that's the main mechanism that we use to control homeostasis. Positive feedback takes us out of homeostasis, because positive refers to giving you more of the same. Okay, so if sodium enters a cell, that might trigger the cell to allow more sodium to enter. Okay, so we're accelerating the process of sodium entering the cell. So positive feedback, again, doesn't maintain homeostasis because it gives us more of whatever the change is. So it actually brings us out of homeostasis, but we can tolerate that. Sometimes we need to be out of homeostasis for short periods of time, but eventually we'll always bring it back to homeostasis. We'll have mechanisms for that. Okay, so let me give you some more examples of negative and positive feedback. Okay, and how they work. So negative feedback occurs in a loop. Okay, again, and I put that right underneath negative feedback. It's the primary type of homeostatic control. Okay, and the reason is because it opposes or reverses the initial change. So in order for negative feedback to occur, your body needs to be able to detect that a change happens. Okay, and we do that through sensors. They're usually associated with our nervous system. We have sensors all over our body. We have sensors that can detect temperature, that can detect oxygen levels, that can detect blood pressure, all the different things that we talked about. And so that sensor, all it does is detect. It doesn't really analyze if something is going higher or lower. It just detects, and it brings that information to a part of the body that can understand that situation. That's called the integrating center, and that's almost always the brain. And specifically, it might be the hypothalamus in the brain. Okay, so as the sensor, the nerve is bringing that information to the hypothalamus, it's the hypothalamus that can determine, All right, now the information I'm getting from the sensors on temperature is that temperature is increasing. So the hypothalamus now is going to send out a signal to an organ that can reverse that change. That organ in general is called an effector. The effector is the organ that produces a response to reverse the change. In my example of temperature increasing, the hypothalamus is going to send a signal either through nerves or hormones, causing your sweat glands to increase their activity, produce sweat. So when you sweat, you get a layer of water on your skin, and that evaporates, and when it evaporates, it carries heat with it, and so you cool down. Right? So when you cool down, you've reversed the change. There's your negative feedback. The loop comes in because the sensors are going to detect that change, send it to the integrating center, and the integrating center will determine, well, we've brought the temperature back to homeostasis. So that integrating center now can inform the effector to stop performing, stop sweating. You don't need to sweat anymore. Okay, so center, integrating center, and effector. You need to understand those three components of negative feedback loops. I'm going to give you another example, let me continue with this example. So we talked about increasing temperature. So let's say now you start to decrease in temperature. Again, the sensors are going to detect that there's the temperature, what's occurring in your body. It's going to send that information to the integrating center, your hypothalamus. It's the hypothalamus that's determining that it's getting too cold. Okay? And it will send a signal to the effector. In this case, it's a different effector because you want a different response. In this case, the effector is your skeletal muscles. And your skeletal muscles will start to twitch. They start to do these small little contractions. Okay? And so if you recall from general bio, your skeletal muscles need ATP in order to contract, to twitch. Okay? When we convert energy into ATP, we lose some of that energy as heat. Well, we mammals take advantage of that. We shiver, we use the heat to increase our body temperature. Brings us back to our set point. And then the hypothalamus can tell us we don't need to shiver anymore. Negative feedback loops. Okay? I'm going to keep throwing examples at you. Here's another example. Let's say you just ate a big meal. And one of the nutrients when you eat is glucose, right? A carbohydrate. We have to maintain a certain amount of glucose in our blood, but after you eat, it raises your blood glucose level. You don't want to have too high blood glucose level. That can cause damage to blood vessels and things. We'll learn more about that later in the semester as well. So we detect that blood glucose levels are going up. It sends a signal to our pancreas to release a hormone called insulin. So insulin now is what signals the effector to take up glucose. And the effector could be liver cells, the effector could be fat cells, it could be other cells in the body. Okay? But when the cells pull glucose out of the blood, what happens? Blood glucose levels go down. We just reversed the original condition. High blood glucose went down to, we lowered blood glucose. And so that's negative feedback. The feedback part becomes when we detect that blood glucose is falling down to normal levels. And so we'll stop this loop. We will stop this chain of reactions. The pancreas will stop releasing insulin. Okay, now let's say you've gone a while without eating. And so you can go a little while without eating because we have a certain range of glucose in the blood. That's why we do that. But if you go too long, blood glucose levels start to fall. You don't feel good when that happens. So the body detects it, causes our pancreas to decrease the amount of insulin because we don't want to take glucose out of the blood anymore. But it will increase the amount of a different hormone called glucagon. Glucagon. So that causes these cells, adipose tissue, those other cells, to stop taking glucose out of the blood And it will also cause the liver to start secreting glucose back into the blood. The liver is a great storage organ for glucose. And the effect, blood glucose levels go back up, right? That reverses the original condition. So that's negative. The feedback comes in when the blood glucose levels go back up to normal range. This chain of events will be stopped again. Okay? So that is negative feedback. And again, negative feedback is the most common feedback system. It's the way that we maintain homeostasis because it keeps us within that normal range. Okay? So here's positive feedback. I mentioned positive feedback means we're going to accelerate the change, or it amplifies the original change. Okay, so this doesn't occur as often because think about it. If positive feedback loops kicked in when your body temperature starts to increase, then what would happen? It would increase even more. That's dangerous. We don't want that to happen. Okay, so that wouldn't happen. That just doesn't occur in our body. All right, so it does not maintain homeostasis. Well, when do we use it? When do you want to be out of homeostasis? One of the most simple examples that we can understand right now, I'll give you more examples as we go further in the semester, but one of the easiest ones is childbirth. Okay, so in childbirth, the baby is growing in the womb starts to stretch, the uterus starts to stretch, and the uterus is surrounded by smooth muscle. So when mother gets to about the 9th month, that smooth muscle gets stretched to the point where when it gets too far, it will automatically start to contract, intrinsically controlled. Okay, so the stretch too far will cause it to contract. That contraction is a signal that's sent to the brain, to the hypothalamus. It detects that contraction. And when it does, it releases oxytocin, a hormone. Oxytocin then travels through the bloodstream and it gets to the uterus, to the smooth muscle, and causes it to contract. Now it's extrinsically controlling that organ, right? And causes it to contract. That contraction tells the hypothalamus to release more oxytocin, which causes more contraction. That's what you want to push the baby out. You need the uterus to contract to push that baby out. A contracting uterus is not a normal situation. You don't want that to happen all the time. Okay, so it is temporarily taking you out of homeostasis, but you need to be out of homeostasis in this situation to get the baby out. Once the baby is born, then there's no more pressure on the smooth muscle, so it stops contracting. So the hypothalamus is not getting the signal anymore. It stops releasing oxytocin, and the uterus then will slowly start to relax, and it won't contract anymore. And then you're back in homeostasis. Okay, so the positive feedback loop is what's bringing you out of homeostasis and causing more and more contraction, which in this situation, it's a good thing. You want to be there. Okay. So what happens if there are disruptions in homeostasis? Meaning you're coming out of homeostasis and the body doesn't have the ability to bring you back in. That's a disease state. Okay, that's how illness occurs, or a pathology. That's what we refer to illness as pathology. And if you can't get it under control, then that could cause death over time. So we actually produce medications and things that help us when we lose the ability to control these things. So think about it. What happens when your blood glucose levels remain high and you don't have the mechanism to bring it back down into homeostasis levels, right? Some of you may understand that's diabetes. Diabetes is when blood glucose levels are high, and there's a couple situations. Either you can't produce the insulin to control and bring the glucose levels back down. That's type 1 diabetes. Or your body starts to ignore the insulin that you're producing. And later on, we'll learn why it does that. But that's type 2 diabetes. In both cases, you're unable to control that level of blood glucose. Okay? So the study of disease is called pathophysiology, right? And this is just studying the abnormal functioning that can occur in the body that gets associated with disease, and trying to understand why the organ is functioning in that matter, and then how to reverse that situation, maybe through medication or therapy or something like that. Okay, that's it. That's part 2 of lecture 1. I look forward to seeing you guys in class. Make sure you jot down any of your questions. Thank you very much.